the volume. All right, let's see if this little baby works. So today I'm here for Roger. Actually, I'm Tom Clater. Roger Stringham sitting right back there. He's the originator and the master of this cavitation technique. But what we wanted to do, and I kind of hesitate to do this, but because I tell all my students, and I've had like 34 students at the lab, that don't ever tell a story when you're giving a presentation, because then you'll just take too long. But I'm going to give you the really short story. And that's in 1993, Roger calls me up and says, hey, I've got this cavitation experiment. It's pretty big. It's like this big, a few hundred watts. And can we check it for neutrons, tritium, gammas, whatever else we can do? And I said, sure, come on down to the lab. We'll put you up and we'll run the experiment. So we put him up. He ran the experiment and we saw no neutrons, no gammas, and we couldn't check for helium, and we looked for tritium. We saw a little bit of tritium, but guess what? We were in the ice house, and the ice house is where all the tritium is in Los Alamos. So we kind of discounted that. But later, Roger took that sample, the samples that he ran, took him to Brian Oliver. Everybody knows Brian Oliver. He's the DOE expert on helium analysis. And Brian looked at samples out of that, parts out of that sample, and found some helium, significant amounts of helium. So I put that in the back of my head, and nothing happened. We went on, we did our plasma stuff, we were looking for tritium and things like this. Then a couple of years ago, Roger and I started talking at one of the ICCF conferences, and he's got this little tiny cavitation experiment now, very tiny. And Roger's sitting right back there. Okay, he hasn't seen this presentation, so I hope it's not too embarrassing. He hasn't seen any of this data except a couple of view graphs, and so he may be a little nervous because it could be good or it could be bad. So at any rate, we looked at this thing, and it looks like a nice demonstration cell, okay, for cavitation. But from my standpoint, what I found attractive was that you can very quickly test for any activity in a foil. We used to use powders, we used to use wires. You can't very well make powders as an alloy. I think George Miley knows this. It's tough to make an alloy out of powder. And wires, well, you have to draw them, they get brittle. But if you can make a foil, you can make all sorts of different alloys. So it's easy to test the materials. So that's my interest in this. And I'll say that again a couple of times. So, cavitation had kind of a bad rap because of Taliarkin. And then there's Moss and Mead at Livermore and Lannell, who did these hydro simulations and said, okay, yeah, we can get nuclear fusion, 1 neutron an hour or 1 neutron a day or some fusion like that. But, they don't really have very good equation of states for those sorts of things. So I don't know if you want to really believe it. And then, there's other cavitation experiments. But offline, if anybody knows anything about this Leclerc and the Cardone experiments, talk to me about that, because I don't understand it at all. And then Roger has been very persistent in following up on this and in improving and miniaturizing the system. So our objective here was to actually just verify the heat results of Roger Stringham. In the back of my mind, I want to measure different foils. I want to see if things do give heat or don't give heat, what sort of alloys work better than others. But I want to see some heat. And we're going to collaborate with Industrial Heat. Ed Storms did almost all the SEMs. We did a few at the lab. And Coalescence provided the calorimeters, a very nice Seebeck calorimeter. So all of that, what we do is tritium with the Beckman system, germanium, all these other X-ray detectors, helium-3 neutron detector, we have an optical spectrometer, and PMTs for sonoluminescence. Interestingly enough, we are not at, we don't get any sonoluminescence so far. And that's because we're not real good at this. And then we have an ultra-sensitive helium-4 detection system. And Malcolm's going to talk about that in the next session. That is the system I hope will supplant the one Brian Oliver had. It's actually better than the one that we had at the lab at Los Alamos that we used years ago. Also, Roger has a poster in the poster session which explains a little bit more about this technique. So we have cavitation. I told my story, so I don't have any reason to go into conventional cavitation. What Roger's doing is multi-bubble cavitation in D2O. So these bubbles are collapsing near a metal surface. They're energetic enough to erode those metals, and they're injecting vapor gas, probably from the void into the metal. So why do I care? Why should you care? Okay, this checks off several things. It checks off this, whoops, here we go. Oops, okay, it checks off this high density of hydrogen and deuterium impinging on the metal. It's a non-equilibrium process. We have a rapid distortion of the metal lattice. What was that guy just talking about? Okay, distortion of the metal lattice. And it's a fast way to test various metals or alloys. These tests take just a few minutes, and you'll know the answer, one metal versus another metal. So that's my attraction to this. Maybe we'll see some heat, maybe we won't see too much heat, but we'll be able to hopefully rank the metals. Okay, so this is just a little single bubble cavitation. We don't go through this, but if you look right here at, okay, yeah, I see what the problem is, okay. Yeah, our bubbles are right here, resonant right along this line. They're about 30 microns. And when I was originally looking at the literature, if you want to get cavitation to 1.7 megahertz, which is where Roger's working at, you need about 1,000 watts per centimeter squared, which is impossible to do. And it turns out, nobody just talks about this, but when you add nanoparticles to the system, which happens just as soon as you start running this, it drops to something reasonable like 10 watts. So here's what Roger started out with, and we have a reservoir, a cell, pump. We're going to look at flow calorimetry, and the Stringham cell is very tiny. It's like 1 inch by 1 inch. It's a little cylindrical thing. Yeah. Okay. And here's the water flows in over the transducer and right next to the foil. Well, this turns out to be a really difficult thing to assemble. There's leaks. So we tried it on our Seebeck calorimeter that Coalescence had. I didn't get any results because I was using palladium silver, and I get pretty discouraged. So Roger said, well, we're getting a couple watts out of my system. So what we did was we completely changed it. Okay, so this isn't quite the replication, right? But this is what happens. People change everything. If you've got a couple of watts, you can just do a static cell. You've got the foil in there at the bottom, the transducer, a reflector to mimic kind of that resonant system, and a couple of thermocouples and a stir. All right, so we tried this. We tried with a few foils, and we're seeing something on the order of 5% from one foil to another versus no foil. It's not very much. It's less than a watt, but it was encouraging. So we'll keep on going. And what was happening with that particular system is the foil is flat, parallel to the transducer, and you can put the foil 2 places for the maximum pressure. You can put it up here, right here, or you can put it very close. Roger puts it very close, and when you put it very close, you get pretty aggressive action on this witness plate. So this is a piece of nickel that's coated with paint. And you can see we've blown most of the paint off. And on the other one, you can see some lines there that are actually the wavelength of sound in water, or D2O, and those were at the maximum, the Fresnel focus. So what's wrong with doing this? What's wrong with doing this is that when we assemble that thing, we'll either get something like this, or we won't get any action at all. And it turns out that the way we fixed that was we slanted the foil so you can't miss where the focus is, because the O-ring compresses, everything's a little squishy in there because we've got Teflon gaskets, and the sort of assembly needs to be very, very precise if you're going to get that action at the surface. So here's the copper foil. In the other cell, it's going to go into the calorimeter, and you can see it's slanted, and 10 out of 10 times we get some action on the foil. It's not as much as when we had it precisely aligned. If we could do that each time, that would be nice, but I'm afraid we can't. So Roger's the master. This is what he can get. Okay, pretty aggressive action on the foils. How do we drive these? Well, there's a very simple drive system that he's using. It's a little board. It goes up to about 40 watts, and we have a bigger systems that go up to 150 watts. So we use the small one because what happens is that the transducers can't take it. We have a lot of damage to the transducers if we go up to 80 or 90 watts for a minute. And again, over here is the spectra, so that's about 10 to 20 microns bubble size out. That's how we know we have the cavitation. We have some sound files on that, and then we also have these witness plates. So we finally, after going through about 5 or 6 iterations, got to this point, and I was feeling kind of bad about it because we were, trying to get this reproducibly, and we had problems with measuring the power, and we had different types of cells made and all that. But then I was reading a book. There's a new book on biography of Fermi, and it turns out that Fermi put together something like 87 test cells, okay, before he built CP1. So I don't feel too bad about it. You can kind of see the intensity of this cavitation because that reflector is being chipped off. So. By that intense sound field. Okay, so where do we operate at? Well, we measure the cavitation threshold, and this is kind of an interesting thing here. This is with no foil, and this is with a foil. So we're operating around 20 watts in, and the reason for that is when we operate up here, we can only operate for a few cycles before the transducer's broken. We don't see multi-bubble cavitation. And so these are the variables we have. We're trying to keep everything constant except this thing right here. So we degas the water. This is a free-floating thing because these micro solids come out from the foil. And then we keep everything else constant. So what do we see? Well, we're using this calorimeter now. We feel like everything's pretty stable. We have reproducible cavitation damage on the foils. So this is what we're using, this coalescence calorimeter. You can see that calorimeter right here. We tried Ed's calorimeter, but it didn't work for us very well because of the sensitivity to air currents. And this is what we get. We're going to apply the power for about 60 seconds to measure that integrated voltage. We can get one data point basically every 3.5 hours, so we can run one foil every 3.5 hours. Now, the cells weigh 110 grams, the foils are 150 to 420 milligrams, and then there's 20 grams of H2O or D2O in there. So I expect that the H2O and the D2O results should be similar because of the heat capacity is almost the same, but it's not quite. And there's a significant amount of heat dissipated in the transducer. In fact, the transducer for different foils can go up to about 150 degrees C, depending on the foil. So here's what, this is my my interest is. Okay. We used a low tritium D2O. We kept it 22 watts. And here's the ranking of the foils. So we have this palladium, rhodium, cobalt foil, which works pretty well. Copper. Okay, why is copper so high? I don't know. And then palladium boron's bringing up the next one, niobium, palladium, lithium. We get down here to the bottom, and it's palladium, silver. Gee, I didn't make this view graph up, like yesterday. I made it up a week ago or 2 weeks ago before I knew what Emma was going to say and Mel Miles was going to say. There's also this palladium silver foil we loaded in D2 to 0.55, and that's endothermic because we're deloading it. So after we ran it, we looked at how much it had deloaded, and it deloaded by 3 or so milligrams. So the uncertainty in these results is probably about 2%. This is what we have. The power to the system is about 32 watts, power to the transducer is 22, and then radiated into the liquid, you have to calculate that, and it's maybe 18 watts. So our maximum excess power is 3 watts in this, which is kind of bigger than what we had in the rough experiment. So this is one of those experiments where it got better and the effect's bigger. Okay. And I don't think you'll find too many of those, but that's the action. But I'm still worried that there's some artifact here, so we're going to probably keep doing that. What about the tritium? Okay, tritium measurements, we just filter, distill the water. We can't remove all the particulates. They're sub-nanometer, they're like nanometer size. We have a Beckman 6500, and this is a problem here. We ran that palladium silver sample for 5 minutes. We get this, large uncertainty. Then we ran multiple samples. We're doing a survey, and we get this, and then we run it even longer, and it's not so much. So the tritium, again, is not working out for us. Okay. I want to talk about particulates a little bit. Here's the light scattering. And the initial D2O, you can see, is pretty clean, but not super clean. And then after 76 minutes of various foils, this is in the dark, you can see that the various foils are fluorescing, unlike the palladium, rhodium, cobalt, so we have to do a little bit more work on that. What we're finding in these foils is kind of interesting. This is the palladium silver foil. This is the one that didn't generate any heat, and we find this big rock on the surface. And if you look under the rock, you'll find a hole, and you'll also find sort of a discolored surface around the rock. Well, it contains oxygen, aluminum, everything that you would find in rocks on Earth, basically, except that we have a hole in the palladium, and that hole contains also this material. So is it ejected or not? Yeah. Yeah, I'll try and speed it up because I told the story. And yeah. So at any rate, that's pretty interesting. That was one of the first foils we ran, so we got kind of interested. We ran a nickel foil, and you can see the stripe down the nickel. And what that stripe is a large number of nickel balls. Well, that's pretty interesting too. If you have nickel oxide, you can convert that to nickel by hydrolysis. So maybe that's the low temperature version of this, but I'm not sure about that. Some of the other foils, there's palladium silver again with some aluminum oxide balls. And then this is that copper foil that was up near the top of the ranking. And you can see this is side lit, so this is a little darker. This is the cavitation damage, and then all of this stuff, this little white flecks are iron oxide. Nothing too interesting, nothing radioactive here. This is a palladium boron with side lit, and you can see those little iron oxide bits too, and a copper stripe. And then palladium with many micro holes, which is pretty typical of what Roger would see in some of his systems. I might mention that the reason we went to a Lexan, kind of an all-plastic system, was so we could see this kind of material here. And this is more what you would expect to see rather than rock that I showed you to begin with. This is a zirconium foil with a large iron agglomeration. You can see the individual particles in this system. So what are these? This is our first ICPM analysis. So we have a lot of sodium in the system. I didn't know there would be that much, but apparently there is in our D2O. And nothing really stands out here. Detection limits are, ppm sort of things. And we're still looking at this, so I don't know whether there's anything that can be gleaned from it. I'm a little surprised we don't see more iron. So we're gonna have to run some of these samples a little bit longer. So X-ray and particle emission measurements, we don't see any X-rays or gammas. There's nothing there. We have pretty good equipment for that. RF emissions, we're gonna try that. Helium measurements, again, are interesting. Malcolm's gonna talk about that. And we don't see any post-foil activity in our SSB. And neutron measurements, we'll probably do those soon. So here's our issues. Very little prompt gammas or X-rays from these operational cells. Tritium signal is pretty low and probably not significant. We don't have any evidence for that. No, the big thing that bothers me is this no foil. When we don't have a foil in the system, and it's H2O, that's about 8% different than the D2O with no foil. So that could be some sort of an artifact there. And we don't see any sonoluminescence, but we do get vigorous cavitation. So our wrap-up is that we have an effect that's material dependent. It's probably a near surface effect. That hole you saw is less than 125 microns deep. And this is a non-stationary system. It's very dynamic, probably needs to be tamed. If we can get a little bigger cavitation or more robust transducers, perhaps we can get a bigger effect. But my interest is that it's a quick way to screen alloys and perhaps modifications, and only small samples are required. These are 250 milligrams. So the excess heat is interesting. And are we confirming Roger Stringham's claims? I think so. Roger, do you want to stand up, Roger, and let everybody? Okay. So thank you very much for that. And if you've got any questions, I don't have any answers. Okay.
Thank you, Tom.
Okay.
Maybe we can have 2 questions. It was Tom.
I would like to make 2 points. First of all, the calorimeter that you identified as being mine, that was a commercial calorimeter, and I take no responsibility for its behavior.
Okay, good.
In fact, I used it for a while and gave up and went on designing my own.
And
then I gave it to you.
Yeah.
Right.
Okay,
because
thanks.
You had something worse at that time, but you made it better.
That's right. That's right.
The other issue is that this particular method for initiating the effect falls into a general category of treatments. And the big question is, what is that category? The category seems to be, if you provide deuterium to palladium or maybe other materials and subject them to a non-equilibrium, a stress condition, you get excess energy. And you can do that all kinds of different ways, and this is just one of the various ways that can be done. As I challenge the theoreticians to focus on those variables that seem to really matter and not on what they imagined. So, thank you.
Yeah, so I didn't mention that this probably can be increased by a large amount because the transducer technology can be fixed. We don't need to blow the transducers up in order to get this effect. So.
Okay.
Yes, Tom.
Please.
Tom, excellent speech. Thank you. That was my point. One thing I learned from Suhas Ralkar last year was if you can get the coupling right between your ultrasonic transducer, so that 95% of the energy is transferred, it won't break apart. So it's about horn or whatever. If you want to scale that up and make it reusable, you can then get a much more less energy input, so you can see a bigger signal.
Let's talk offline about
Yes,
that.
that's-
Okay.
I know that Roger operates, I think, at 1.6 megahertz. Is that right?
That's right.
Yeah. I did similar work, not for this purpose, just studying sonoluminescence to NRL about 14 years ago, and we were operating around 20 to 25 kilohertz, and we were about to add to that a over 1 MeV, 1 megahertz signal as a chirp on top of it. Have you considered running essentially a base, setting up almost a standing wave in there, and then chirping on top of that?
Yeah, that's what Moss recommended to increase the output. He also found that vapor additions to the cavitation bubble weren't detrimental. So that was kind of contrary to what people believe. But yeah, he wanted to chirp. I don't know how you do the symmetric chirp, but that's something we can try. Yeah.